this section is on apportionment. Now, what is apportionment? Why would we need it? You'll see a little more while after we work at the first example. But apportionment is basically when you have to apportion a amount of objects across several different entities. So you want to make sure that you're fair. So if you've got, say, 4 elementary schools and you've got to apportion, say, 100 computers throughout them, would it be fair to necessarily divide by 4 and give each elementary school 25 computers? Well, that depends. What if one school only has 100 students and another has 400? It makes a big difference. So that's why apportionment comes in. And there are 4 different methods of apportionment that we're going to look at. One works better in some cases than others. And it's just up to the person apportioning or to decide which one would work best for them. So we're going to extend the concepts of elections to encompass how we apportion resources equally. In the United States, a method of apportionment is used to determine how many representatives each state is allowed. So this is something that, you've probably heard discussions about before, about voting and all, okay? So with electoral votes, for example, each state gets a certain number of votes that depends on the size of the state. It's the same thing with how many representatives each state gets. It depends on the size. So apportionment is the method of dividing resources in such a way as to maximize the use of those resources. If Texas were to divide the available funds of $87 billion evenly among its 104 institutions of higher education, how much would each get? So we would take the funds, 87 billion, there's 1,000, million, billion, and divide by 104. So each institution would get $836,538,461.54. But this is not fair because each institution is not the same size. So that's where apportionment comes in. First thing you need to do with apportionment is find the standard divisor. It's the average number of members of the population that will account for one apportioned item. You find it by taking the total population in the group, divide by the total number of items to be apportioned. That's your standard divisor. It's thundering. A standard quota represents the number of items that will be apportioned to each subgroup. So after you find the standard divisor, you go through each subgroup, take the population of the subgroup, and divide by the standard divisor. So, for example 2, it says, in 2012 Super Bowl, oh Lord, I don't even know I don't know what L is. I had an allotment of about 100,000 tickets. The average price of a ticket was about $900, meaning that the total value of sales to the NFL was a whopping $90 million. The allotment of tickets for each of the groups that were allowed to purchase tickets is given in Table 1. Determine the standard divisor and standard quota for each. Okay, so here's our table. Had to add my last column there. Okay, so we first start with the standard divisor. And so that's going to be the number of tickets sold divided by the total sales. So 100,000 divided by 90 million. 0.001 tickets sold per dollar. So to find the standard quota, here's what we do. We take each amount of tickets here and divide by the standard divisor. So we'll take 35,000 and divide that by 0.001, and we have $35 million. So that's the amount of money that's allotted to each of the Super Bowl teams. Okay? They would split that in half between the two of them. Then for the non-Super Bowl teams, we take the 34,000 here and divide by that same standard divisor. So the non-Super Bowl teams divide among them $34 million. The host team will take 5,000 and divide by the standard divisor and get $5 million. And so forth. Okay. Same type deal for each one here. I'm going to pause and finish this up. Okay. So now we've found the allotment for each of these entities. There's 4 methods, like I said. The Hamilton's method is the first one and the simplest one we'll look at. You find the standard divisor. You find the standard quota for each entity or each state. Round the standard quota down to the next lowest integer. And then award any remaining resources based on which group's standard quota was rounded down the most. That is, whoever had the largest fractional part rounded down. You'll understand that more as we look at the example. So we're going to use the Hamilton's method to apportion the number of representatives for each of these states. So again, the first step is to find the standard divisor. We take the total population, that's 10,000, and divide by the number of representatives, which it didn't tell us in the problem, but I happen to know 100. So the standard divisor is 100. To find the standard quota, we go along and divide the population by the standard divisor of 100. Okay. So the next step is the minimum quota. We just take each of these and round down. And then the next step is to write the fractional remainder. Well, no, before we do that, we need to add these up. 9 plus 27 plus 26 plus 37 adds to be a total of 99. If that were 100, the number of representatives, we'd be good to go. But it's not. So what we do is this. We look at each fractional remainder. We have 0.63, 0.26, 0.03, and 0.35. And we take the largest ones and round up until we get to 100. Well, since it's 99, we only need to use the largest. That's this one. And so we can take that one up to 10, and everybody else stays the same. And so that is our final apportionment. 10 for State A, 27 for State B, State C gets 26, and D gets 37. So that was Hamilton's method. The next two methods use what's called a modified quota. It's a divisor near the standard divisor that's chosen by guess and check in an attempt to make the sum of the modified quotas exactly equal to the number of items to be proportioned. Yes, it's guess and check. And so doing these by hand could be extensive. So I want to show you at the end here how we would do these in Excel and how to set that up for yourself. So the Jefferson's method, find the standard divisor and all the standard quotas, round them down. If there's any leftover things to apportion, we need a new divisor. So we change our standard divisor to a modified divisor. Then calculate the modified quotas with the modified divisor. If we still have leftover things to distribute, try again and continue to try again and again until you get it right. Yeah, fun. Suppose that a university has 18 scholarships to be apportioned among 225 math majors, 417 history majors, and 308 computer science majors. Use the Jefferson method to determine how the scholarships should be apportioned among the three major groups. So, let's first find our standard divisor. It will be the total number of students divided by the number of scholarships. Let's see. So the total number of students would be 225 plus 417 plus 308. That's 950 students. So the standard divisor is 52.778. Then we find each standard quota, just as we did before. So we'll take 225 and divide by 52.778. For this first one, we get 4.263. For the second one, we take 417, divide by 52.778, and get 7.901. And then the last one, take 308, and divide by the standard divisor. And we get 5.836. Round each of these down. And let's see, when we add them all up, we get 16. But there's 18 scholarships. So, the next step is to come up with a modified quota. And so usually what we'll start with is with Jefferson method is to round down. So I'm just going to round each of these down to 52. We were using 52.778. So we're going to round down to 52. And so I'm going to do the same thing as above, except I'm dividing by 52. Okay? Okay, and again we go through and round down. So this time, when we total, we get 17. Well, that's definitely closer, but not quite there. So we need to do this one more time. So this time, we're going to choose a modified quota of 51. So same deal. And round each of these down. This time, when we add them all up, we get 18. So our final apportionment is 4 scholarships to math, 8 to history, and 6 to computer science. Webster's method. Start with the same thing. Standard divisor, find all the standard quotas, round down. If the sum of the quotas is not equal to the number of items to be apportioned, then we modify the divisor. Calculate again. But with Webster's, we round the modified quotas to the nearest whole number. So we could round up in this case and can continue to modify as needed. Oh, we should read the problem. A computer tech firm has 3 divisions with 135, 98, and 132 employees, respectively. A total of 12 administrative assistants must be allocated to the 3 divisions according to their size. Use Webster's method to determine how many administrative assistants should be allocated to each division. So first we need our total. Add them up. 365, and then we can find our standard divisor. That'll be 365 divided by our administrative assistants. So it gives us a standard divisor of 30.417. So we're going to go through and divide by 30.417 just like we did before. 135 divided by that is 4.438. 98 divided by that is 3.222. And 132 divided by our standard divisor is 4.340. First, we round down. And we get a total of 11, but we need 12. So we choose a modified quota. The book tells me use a modified quota of 30, so let's try that out first. Oh, it was supposed to be 98. Sorry. I was wondering why it didn't come out even. Now we're free to round up or down depending. So the first one, 4.5, will round up to 5. The second one would round down to 3, and the third would round down to 4. And that adds to give us 12, so we're good to go. The last method is different. We start the same way, but we use a geometric mean. The geometric mean is the square root of two numbers multiplied. So the Hill-Huntington method says find all the standard divisors and all the standard quotas. Find the geometric mean of each standard quota. If the geometric mean is greater than the standard quota, round down. If it's less, round up. If the sum of the quotas is less than what we need, we modify the divisor. Then find all the modified divisors, or find all the modified quotas, find the geometric mean again, and continue. Suppose we are dividing 100 seats among 5 states with the following populations. Okay, so here's our 5 populations with a total of 75,000 people. So our standard divisor will be 75,000 divided by 100. And so that is 750. So with each of these, we're going to divide by 750. I'm not going to write it out this time. So 35,589 divided by 750 is 47.452. The next one when we divide by 750 is 23.233. Next we get 4.877. Then 15.276. And 9.161. So the next step is to find the geometric mean. The geometric mean would be rounding down and rounding up. The square root of the rounded down number times the rounded up number. So for this would be 47 and 48. So we do the square root of 47 times 48. That's 47.49, I think that's a 7. So for B, we would do the square root of 23 times 24. That's 23.495. This one would be the square root of 4 times 5. This one is the square root of 15 times 16. And last, the square root of 9 times 10. Okay, so we gotta go back. I'm gonna go back and read these rules again. If the geometric mean is greater than the standard quota, round the standard quota down. So in this first case, the geometric mean is greater than the standard quota by a little bit. So we round down. And the second one, it's greater, so we round down. And the third one, it's less, so we round up. For state D, it's greater, so we round down. And for state E, it is greater, so we round down. So let's see, what do we get when we total those? We get 99. Not good enough. We need to apportion 100. So we do it again with a modified divisor. Book tells me use a modified divisor of 749. And we're going to go ahead and use that one because it knows it works. So here's the numbers we get. Well, hello, kitty. When we divide by 749. Finnick, run along. He's saying hi. And that would be his bell because he has to wear that to keep from killing too many animals. And we go through and do the geometric mean thing again. Are these not the same numbers? Sure does look like it. Yeah, so, because it's still 47, notice. So it'll still be the square root of 47 times 48. This one's still 23. So it'll still be, or 23 there, 23 times 24. Yeah, and that one's still in the 4s. This one's still in the 15s. I'm just using the same geometric mean because they all seem to be the same numbers, square root of numbers multiplied there. But the difference will be where we round. So remember, if the geometric mean is greater, we round down. So in this first one, the geometric mean is less. So we round up. In the second one, the geometric mean is greater, so we round down. For state C, the geometric mean is less, so we round up. For D, the geometric mean is greater, so we round down. And for E, the geometric mean is greater, so we round down. And this time when we add, we get 100. So state A gets 48, B gets 23, C gets 5, D gets 15, and E gets 9. Okay, and the last part of this, we're going over a few things that can happen when you apportion. The quota rule implies that any fair apportionment method should assign to every group either its lower or upper quota. So what this is saying is that if you look back at the standard quota, all of these numbers should either be one number greater or one number less. So the first one has to be 47 or 48. The second one has to be 23 or 24. The third one has to be 4 or 5, and so forth. That's what the quota rule says. The Alabama paradox occurs when an increase in the number of available items causes a group to lose an item, even though the populations remain the same. So the populations could be the same, but say the number of representatives went from 100 to 101. And so that makes one group gain and it makes another lose. That's just something that happens sometimes with apportionment, and that's called the Alabama paradox. The population paradox states that Group A can lose an item to Group B even when the rate of growth of the population of Group A is greater than Group B. The new states paradox happens when the addition of a new group with corresponding increase in the number of available items can cause a change in the apportionment of items among the other groups, either up or down. So example 7. After the 1880 census, when the population of the United States was found to be this number, a little over 50 million, the chief clerk of the United States Census Office computed the number of representatives to either be 299 or 300 seats. According to the 1880 census, the population of Alabama was over 1 million. Find the standard divisor and standard quota when there are 299 seats or 300 seats. Okay, so the standard divisor is the U.S. population divided by the number of seats. So we're starting with 299. So there's the standard divisor for 299. And then the standard quota would be the Alabama's population divided by that standard divisor. So the standard quota would be 7.52 seats. For B, the standard divisor will be the U.S. population divided by 300. And so the standard quota would be Alabama's population divided by that standard divisor. .55 seats. It's hard to see what it's talking about here with the Alabama paradox, but basically, if you've got other states factored in here, then it could happen that in the first case, we would round down to 7, or say up to 8, but in the second case, we might have to round down to 7, so Alabama would lose a seat. So that's the idea. Okay, we'll include some Excel in here to finish up. These in Excel, because especially when we start getting into the last 3, this makes things a lot easier. Okay, so we've got our information here. We can find the total scholarships by saying equals, or the total population by adding these 3. That was 950. And then the standard divisor would be equals that number divided by the number of scholarships, which was 18. Okay, so there's our standard divisor. So to find the standard quota under math, we would put equals this number under math divided by. Now here's a little trick. I want to be able to drag this to the right, and I want to be able to, for Excel to accept math and then history and then computer science numbers on the top, but then to accept the standard divisor on the bottom without moving it. Okay, I want to keep the standard divisor the whole time. So if I want to keep that number in cell H2, I have to type in a $sign H2. And that's just how you have to do it. Why they chose $sign, I don't know. But the $sign tells Excel to stick with that cell. Okay? So we hit enter and we see that we got the same number we did on our paper. And now I can take this little corner and drag it over, and it's going to give me all three of them. And if I select on this one under history, you see how it took C2 this time instead of C1, but it kept cell H2 on the bottom. Okay, so we round down, and I'm just going to go through and type these in. So 4, 7, and 5. And we can add those. We get 16, which wasn't enough because there were 18 scholarships. So we choose a modified quota. I'm just doing some color coding here. And so we'll make this blue. And our modified quota, we decided to be 52. Okay? So what we do is same thing as we just did above. Equals, take our math, divide by, and this time we want $sign cell H3. Okay? Drag it over, round down, add them up. Still too low, so our next modified quota we chose was 51. Basically, all you really have to do here, if I want to just get rid of this, all you really got to do, to tell you the truth, is change the standard divisor. So change it to 51 or 52. There's how our numbers changed. Change these numbers, 4, 8, and 5. There we see how the total changed to 17. We want to go down again, 51 for the standard divisor. We'll go through, change that 4, 8, and 6. We can see that our total changed to 18. We're good to go. Example 5. We'll do the same thing here. Not even worry about doing it separately. Okay, so this time we had this situation with a computer tech firm, and we need to find the standard divisor first. So I'm going to find the total, 135 plus 98 plus 192. That was 365, so equals 365 divided by there were 12 administrative assistants, so there was our standard divisor. So the standard quota would be equals this number here divided by $sign, and that's H2, cell H2, return. Now I can drag it over, then round down. And there is a formula for rounding, but I'm not going to worry about that. So equals, and we're going to add these three. And I am selecting the cell so that it'll change for me when we change our standard divisor or our modified divisor. So there's 11. We wanted 12. So we choose another number. We chose 30 in the book, so I'm just going to put 30 there and then go through and round. It said we could round up or down with the modified quota in Webster's method. So we have 5, 3, and 4, which gives us 12. And then for example 6, this was our situation with the Hill-Huntington method. And so first find the standard divisor equals our total divided by, there were 100 seats to be apportioned. So our standard divisor ended up being 750. So our standard quota was equals our number there divided by $, and this is cell, the standard divisor is in cell J2, and we can drag it over. Then the geometric mean, maybe I should have left everything down here. I think I needed to. Let me put that down here real fast. Because I'm not using a formula to find certain things here. Okay. So the geometric mean would be the square root. Now, how do you do square root in Excel? It is to the 1/2 power. Okay, square root, if you remember your exponent rules, is equivalent to an exponent of 1/2. So we'll do 47 times 48 to the 1/2, like this. Okay. Return, and we can bring that across. So the rounded standard quota, remember, and again, you could put formulas in here, but you know, we'll do some of it in our head. If the geometric mean was greater, then we rounded down. If it was less, then we rounded up. So here we round down. It's greater, so we round down. Oh, something's wrong here. Oh, I can't just drag it. I have to put it in each time. So equals 23 times 24 to the 1/2 equals 4 times 5 to the 1/2 equals 15 times 16 to the 1/2. Did I put that in right? Nope, 15. And equals 9 times 10 to the 1/2. Okay, there we go. So it's bigger, so we round down. Geometric mean is smaller, so we round up. Geometric mean is bigger, so we round down. Geometric mean is bigger, so we round down. Let's add them up. That's, where did I lose it? Let's try that again. Oh no, that's right. And then we need F5. I was looking at the E here. So F5, enter. Got 99. So we need to change it. Okay, so let's see. We decided to use a modified quota of 749. So we go through equals our number up here divided by our modified quota. So this is a bit more work because so we're going to have to, forgot my $sign, $J3. We're going to have to go through and do the geometric mean again. If you figure out a formula to use, go right ahead. Actually, it was all the same, wasn't it? But this time, we're comparing this number up here, okay? Let's highlight that for a minute. Okay, so geometric mean is bigger, so we round down. Geometric mean is, wait a minute, this one to this one. Geometric mean is smaller, so we round up. The geometric mean, I've got the wrong thing highlighted. That's what we're supposed to be looking at. Okay. The geometric mean is bigger than this number, so we round down. The geometric mean is smaller than this number, so we round up. The geometric mean is bigger than this number, so we round down. The geometric mean is bigger than this number, so we round down. And let's see what we get. What's that? F7. Oh, how it does that. There we go. We got it. Okay. So hopefully showing you how to do these in Excel will save you a bit of time.